Hello. Today we are going to study about ensemble methods. What are these? What are the properties? What are its types? Everything. So whenever you look at the word ensemble, it means a group or a combination of something. That means ensemble, right? So I have written this way: a group or a combination. So in machine learning, these are enhanced version of decision trees. These are the models which are generally used in the real world scenarios, real project scenarios, especially if you look at the hackathons or the competitions. These are widely used. Now in order to explain this more, let me come up with an example. Let's consider a scenario that we are in year 2021. Cool. That's the year where we have COVID. Now suppose you got sick. When you got sick, you consult with the doctor. You go to a doctor and doctor says you have COVID. Obviously you don't want to listen the word COVID when you are in 2020 or 2021, especially. We know this very clearly, right? But even if you have even 15 to 20 years of trust with the doctor, you are not able to trust his predictions, whatever he is committing now. So in response, what you will do? So in response, you consult with doctor 2. So you go to the second doctor and wait for all the tests results. Assume the doctor 2 also declares that yes, you are infected by COVID. Now chance of you having COVID increases because chance of both the doctors going wrong are very rare, right? So what we did with this small use case, we understood the reliability of the prediction that came from the doctor 1 increases because medication from both the doctors might be different, but when the results came out, those predictions we have to trust, right? This is the exact same thing we generally do with ensemble models. Okay, we take the multiple opinions and we then consider the majority, and that's our final output. To explain this further, let's take one simple example as well. Suppose you go to a bank ABC, and this bank, they use decision tree model. You must be very familiar with the decision tree model. Okay, now they use decision tree models in order to decide whether they should lend a loan to a person or not. Okay, this is a classification model which gives the prediction in the form of yes or no. Yes is the person, thus they should lend a loan. No, that means they will reject the application for the applicant, right? Now suppose out of 100 applicants or the customers, you are one among them, and assume this model has 98% accuracy. Assuming 98% accuracy, but still the model says the bank rejects your application, right? But if the bank rejects your application, what are your next steps? You will still say, okay, might be because this model has 2% error scenarios, so there are possible or high chances that my prediction is not accurate. Then what you will do? Okay, pass my data to different other models, this time some different decision tree, then check the prediction. Might be yes, might be no. Even if we are not satisfied with the predictions coming from the both models, we might test with different other models. So this way we are taking the multiple opinions, right? So we take majority. We take majority to increase the reliability. Okay, very simple, because this way we understood chance of multiple models going wrong on the same case will be very rare, will be very less. Okay, so this is the same thing we will be doing with ensemble models. We'll get use case, we'll pass the data to multiple models, and these models generally we are saying the base learners. Then we'll take the output from each different models, and then we'll see a majority, and with that we'll decide whether what should be the right output. Now this, I'm not saying that this is explicitly for regression or classification. It depends what is the use case we are working with. Typically it depends on those aspects as well. Now there are 4 variants of ensemble models. Okay, first one is voting, second one is stacking, third one is bagging, fourth one is boosting. Right? Now let's understand voting. What is voting? This voting, this is further classified into 2 different models: soft voting and hard voting. Hard voting or majority voting. Okay, majority voting is what we just discussed, right? Like we'll take the results from multiple models. We'll see the majority class, and that's your final output. But soft voting, that's the same thing we just discussed. But when we discussed about the soft voting is a little different. In case of soft voting, it looks into the probability distribution of the output. For example, let's assume the same scenario. We'll consider the same scenario for a doctor. Now, you being a patient, you go to a Doctor 1. Doctor 1 says, you being a patient, you go to a doctor, where Doctor 1 says, okay, you have COVID. But you are not satisfied with you can't trust the doctor being declared as COVID. You go to Doctor 2. Now Doctor 2 will say, okay, you don't have COVID. You also COVID. In order to take a final decision of confirmation, you go to a Doctor 3. Suppose Doctor 3 says this, you have COVID. Now what is the final output I should take? Okay, in case of majority voting, I'll say, okay, both my predictions, I got COVID, so that means that is the final conclusion. Yes, I have COVID. Or doctor will say, okay, because we have passed your data to different other models, so that means you have COVID. Okay, but in case of soft voting, suppose in order to decide or declare that yes, you have COVID, doctor says, they are declaring COVID by looking at the temperature they have captured. Okay, suppose the doctor, before declaring that yes, you have COVID, they have checked the temperatures in order to declare. Suppose they said you have COVID based on 90. Suppose you got 99 degree temperature, that means you have COVID. Doctor sees your temperature, and that time your temperature was 92, that means he says you don't have COVID. Another time around 97 or 98 degree, assume it could be anything. Now in soft voting, in order to take a decision, we will do the averaging of these 3 temperature values. Whatever we'll get, 9 to 7, something around 96. Okay, based on 96 degree, we will decide, or we will predict the patient have COVID or not based on this specific value. This is in the case of soft voting. Okay, got it? We have 2 votings, hard voting and soft voting. Hard voting will only look at the majority count, but in case of soft voting, it will look at the probability distribution of the output values. Like it will actually consider the scenarios why the doctor is declaring a patient as COVID or non-COVID, and then it will do the averaging on all the models. Okay, now the second variant in ensemble models is stacking. What is stacking? Stacking generally means piling up. Output. That means the piling up. Okay, that means it uses layers technique to do the prediction. It uses layers technique to do the prediction. Suppose generally when we are doing a prediction, we have multiple features, x1, x2, x3. These are the input values, and we have the final set of variables. Okay, in stacking we have multiple, we pass this data to different other models. Suppose we are passing to model 1, model 2, model 3. Okay, now in generally we in stacking we are saying these models as base learners. Okay, now with each, whenever I am passing this data to different model, to model 1, I'll get one prediction. That means suppose I am getting y1 hat. When I pass the same data to multiple model 2, I'll get this output y2. When I'll pass the same data to model 3, to the third base learner, I'll get output as 3. Okay, that means I'll get 3 predictions. What we do now is we'll take these data points as in the form of inputs, y1, y2, y3. We'll consider the same output. Okay, to create the another data set, we'll create the another data set, we'll create the another model, and this model we will be will be saying as this is the meta model. So output that we are getting from the base learners, okay, the output we are getting from the base learners will become the input to the meta model. So this is the simple thing we generally do with stacking. Okay, stacking means piling up. We'll have a simple, we'll pass the data set to different models, we'll get some predictions. Those predictions will consider in form of inputs to, and we'll use the same output variable or the target variable. Then we'll form a meta model. Okay, the inputs from the base learners will pass as an input to the meta model, and this will be my final data set or the final prediction model, and the predictions coming from the meta model are my final predictions. So this is we generally do in stacking. Now third is bagging. Bagging and boosting, both algorithms, these are the most used algorithms when we talk about the real world projects or and real case study scenarios. So these both algorithms are majorly used. They both are, bagging and boosting, both are tree based algorithms. Okay, and what we do with tree based algorithms is we deal with subsamples. Okay, we deal with subsamples, and we pass these subsamples to multiple decision trees. Okay, this is the case how we deal with tree based models. Now when I'm saying bagging is generally known as bootstrap aggregation. Okay, bootstrap aggregation. Why? Because you will get to know in some time. Bagging, when we say about the bagging model, it is random forest is one of its kind. Random forest is also known as, is also worked on the principle of bootstrap aggregation. Okay, now what happens in random forest is we'll have a complete data set. Okay, as I was telling you, in case of bagging and boosting, both we deal with subsamples. Okay, when I'm saying subsamples, that means there are subset of rows, subset of columns. That means few rows, that means there is a resampling of rows and columns. They will be passed to one model. Suppose this model is decision tree. Okay, and when we say random forest, the base learner model is always going to be decision tree. Okay, this is the complete data. This data, the subsample of the data will be passed to one model. Then the data which was passed to decision tree 1, now a few same number of rows, same number of columns might be passed to model 2, or in the similar fashion, we will be passing the same data, same sampling subsamples of rows and columns to multiple decision trees. It depends on the hyperparameter, or also like what trees we are playing with. Then what we'll do is, for example, this is the scenario. Now we'll take the prediction from each decision trees. Suppose it is saying, consider the scenario where the tree is predicting whether the student will be pass or fail. Suppose this tree says yes, this says no, and this says yes. At the final stage, we'll pass the voting classifier. In case of classification models, we'll take the majority votes, and when we consider the majority vote, yes would be the final output. It depends what is the use case we are working with. For classification, we'll do a voting classifier. In case of regression, or we'll do a averaging out at the end, and then we'll take the final value as the final output. Now this aggregation, when we are aggregating the output at the final end, this is the same thing I was mentioning, that we are doing the aggregation, bootstrap aggregation. Okay, we have the complete data. We'll take a subsample of rows and columns. We'll pass those subsamples to different decision trees. We call these decision trees as base learners. Okay, now we'll collect their output. We'll pass the voting classifier. We'll check output. We'll pass the output to the voting classifier, and from their end, we'll check. The final prediction will be the final output. Okay, this is what we do is in case of bagging. Now let's try to understand what is boosting. That is the fourth technique, the fourth variant of ensemble models. As I mentioned earlier, in the case of bagging, that works on a parallel approach. We will take the data points, we'll pass data to multiple models, and we'll take the majority count, and we'll get the final output. But the approach in boosting is slightly different. In boosting, we follow the sequential approach. Okay, how data is trained on boosting is, okay, the first thing is generally the process which are involved. We say we'll first train a weak model. How we'll train the weak model is, we have the data. Okay, the first model is trained on this data, and this data, or the base learner, it could be decision tree. It will make few of the correct predictions, and it will also make some mistakes. Those terms we are saying errors. So data, this will pass to decision tree. This will make few correct predictions. It will also give some incorrect predictions in the form of errors. Now, in case of boosting, our major focus is on the mistakes or the error points. Now, in the second model, okay, the second model, this time we will train the second model, but this time it will give more importance to the mistakes done by model 1. Suppose this was the decision tree model 1. It had make few of the error points. Now the same data, I mean, of course, newly added data points, this will be passed to model 2, and all the error terms which model decision tree 1 made, they will also be included. Okay, so that is the second step. First one was, the first model is trained on the data. Okay, it will make few of the correct predictions but also make some errors. Then in the second scenario, the second model is trained, but this times it gives more importance to the mistakes made by model 1. Okay, what is our final goal? The goal is to correct the errors that we have made from the decision tree 1. Now we'll repeat the process. The step 3, we'll keep repeating this process. Third model also, this model is trained. If I am saying the data, it will also make a few of the correct predictions. It will make some mistakes. So it will generate some errors. Now, in case of third model, Okay, the third model is trained to correct the mistakes made by model 2. So this process continues for many models, and each model will be improving the mistakes made by the previous one. And the final step will combine the all models. Got it? That means all the weak models are combined in a weighted way to make the final prediction. Or I can say we are actually giving more weightage to the predictions that were wrongly made. In the first model, we had few of the correct predictions, but we actually put some more weightage to the predictions wrongly made by the model 1. In the second model also, we are more focused on the error points. This way, we'll keep improving the predictions that are wrongly made, and the final model is much stronger and more accurate in terms of results than any single weak model. Okay, so this is the overall idea of boosting. Now I hope you get the idea how things are working in case of ensemble models. So there are multiple models. When we say in case of bagging itself, in case of bagging we have random forest is one of its kind, and in case of boosting there are majorly multiple types of boosting techniques. It could be ADA boost. Okay, in case of ADA boost, what we are doing is we will follow the same approach. That means that in sequentially we'll keep training the models. We'll keep updating the weights for the predictions that were wrongly made. Okay, in case of ADA boost, we'll give more weight to the wrongly classified points. We have gradient boosting. What we are doing in gradient boosting, I'm just giving the overall scenario. Again, in gradient boosting also, we'll keep improving predictions by reducing the errors. Here we actually works to reduce the errors step by step. Reduces errors. Then we have XGBoost, and this is the most commonly used algorithm. This is the complex algorithm, but this is widely used in one of the in the real world projects or competitions, because it is fast and it is the optimized version of gradient boosting. We also have light GBM. Okay, this is also fast and it actually uses less memory, and that's why when we have the large data sets, the light GBM is more preferred. One of the last algorithm in this category, you can also work for cat boost. So I have mentioned there are generally, in case of bagging, we have one algorithm that works on the bootstrap aggregation, but in case of boosting we have ADA boost, gradient boosting, XGBoost, light GBM, and cat boost. In cat boost, generally you can assume basically it works well with categorical data. For example, we have the target like we have the features called, if something called colors, different colors are available, some different brands are available. So whenever we have the categorical data, this cat boost algorithm is preferred. You can assume the word name cat here. It's actually referring to the categorical variables. Okay, so I think this is the final summary in case of boosting. So they are combining multiple weak models to create strong model, and each model here is learning from the mistakes of the previous one, and that is how it is actually improving the accuracy, and that's why they are more powerful. Okay, I hope you got the explanation for all the ensemble models here. I hope you like the video. If you like the video, please hit like the share button, and do comment if you have any doubts regarding the use case. Thanks. Click and subscribe.